Hey, Algebra 2. Today we're going to talk about real life situations and how to choose a model. A model would be a type of function. What type of function will we choose to model the data, the situation? By function or model, we mean, will it be a linear model, quadratic, exponential, or sinusoidal. Okay, and we'll go through some steps on how to pick which one of those models which one of those functions that we would use to sort of, model our data. I need a better word than model. Hopefully I'll get that as the lesson goes on. All right, so as our opening exercise, you're working on a team to analyze the following data gathered by your colleagues. They're just a bunch of points, right? Your coworker Alexandra says the model you should use to fit the data is a sinusoidal model. Sketch Alexandra's model on the axis at left on the next page. Hold on. So I already sketched it. I put the points in. This right down here is the negative 1.15, and here is Alexandra's model. Here's the graph that she found that modeled the data. Okay, ignore the quadratic one. All right, as you can tell, it hits every single point perfectly. I missed one. There it is. Okay, next, how does the graph of Alexandra's model relate to the 4 points? Is her model a good fit for the data? It seems perfect, right? It hits, it goes straight through or close to all the points, so a model fits the data really, really well. Another teammate, Randall, says the model you should use to fit the data is a quadratic model. Oops. So I sketched that one right here. And as you can see, it hits the points spot on or pretty darn close. I left D out. So how does the graph of Randall's model relate to the 4 points? Is his model a good fit? It seems perfect, again, right? It fits the 4 points really, really well. It seems to model the data just about perfect. But the two graphs are so different. Which one do you pick? Suppose the 4 points represent positions of a projectile fired into the air. Which of the two models is more appropriate for the situation and why? Well, I mean, if you're standing somewhere on the ground and you shoot a basket, or throw a basket, or throw a baseball, or whatever, it certainly isn't a sinusoidal function, right? I love that word. It's so fun. Okay, that's not right. It's an arc, which is quadratic. A quadratic curve is more appropriate. In the context of the problem, the quadratic definitely makes more sense. It's not cyclic. I'm trying to figure out more words to tell you guys. It's not cyclic, so therefore it's not sinusoidal. It doesn't go back to the beginning, right? So in general, how do we know which model to choose? In this case, we don't, because we don't know the story. Behind the data. So now I'm going to go through some of my notes, right? In this lesson, we're going to focus on, and I've already told you this, linear, quadratic, sinusoidal, or exponential models. some things that we're going to need to think about to pick our model. What is the end behavior of this type of function? How does the function change? If the input value, x or t would be time, increases by 1 unit, what happens to the output value? That'd be the domain and the range. Is the function increasing or decreasing, or does it do both? Are there any relative maxima or minima values? And what is the range of the function? So these are all the things that we need to keep in our mind as we pick the model that we're going to use to model the data. All right, the next few slides are just going to be a bunch of notes. So find a little spot on your classwork or grab a sheet of notebook paper if you'd like to take notes. This is how we're going to decide which model to use. So what are the characteristics of a non-constant linear function? So if x increases by 1, then y changes by a fixed amount. That would be that linear function where we have y equals mx plus b. So if x increases by 1, y would increase by a fixed amount. That would be our slope. Also, the function is always increasing or decreasing the entire time of the model, okay? And it's always increasing or decreasing at the same rate. That'd be your slope, right? We don't have a maxima or minima because it's a linear function. It's always increasing or always decreasing. The range would be all real numbers. Remember, range is your y value. So if we have a linear function, our y values would be all real numbers. End behavior. Is that the function increases all the way to infinity in one direction, and to negative infinity in the other direction. We can't say what direction because we don't know what the function is doing. So what are the characteristics of a quadratic function? If you remember, when we first started learning about quadratic functions, it seems like ages ago, we would have a list of data, all numbers. And we would find the first differences, subtract those two and get a number. And we'd find the second differences. And when the second differences were the same, then we knew it was quadratic. So that's one characteristic of a quadratic function. I know we're really stretching back to something we learned early in the year, but it was second differences. And when the second differences are the same or constant, meaning that if x increases by 1, then y increases linearly with x, then we know it's quadratic. Okay, more characteristics. So the function increases and decreases. Okay, quadratic function. Now, it doesn't matter if it's upside down or not. So that's quadratic, and this is quadratic. Changing direction one time. It only changes direction one time at either the maximum or the minimum. Therefore, it has either a maximum or a minimum, depending on if it opens up or opens down, if the quadratic graph opens up or down. The range is either negative infinity to a, which would be the maximum, or a to infinity, which would be a minimum. A would be the minimum. And then end behavior. The function could increase to infinity in both directions if it opens up, or decrease to negative infinity. Oops, I don't need to write infinity twice. To negative infinity in both directions if it opens down. All right, how about characteristics of a sinusoidal function? Periodic. Okay, the function is periodic. It repeats over a fixed interval. There is one relative maxima and maximus, that's funny. Maxima and minima for the function, and it's periodic, so it repeats. That means we alternate between the maxima and minima. The range of the function, we can say it's a comma b for real numbers. A is less than b. That just means that our range, which is always our y value, is going to hop between and b. That's a b. We have our maxima and our minima, and then end behavior. There really isn't a solid end behavior because it bounces between a max and min as x approaches infinity. So as x approaches infinity, or x approaches negative infinity, the end behavior is just it bounces between the maxima and the minima. And then lastly, our exponential functions. Let's say the function, it increases or it decreases at a rate proportional to the current value of the function. And that'll make sense as we go through an example. If you remember, exponential functions, they look like that. That would be increases, decreases, it's whatever we're doing. Also, the function flattens out. In one direction and approaches either negative infinity or infinity in the other direction. Okay, that's what I sort of drew and erased. So I flatten out and I approach negative infinity in the other direction. Okay, or I flatten out and I approach positive infinity in the other direction, just as an example. Okay, I think this is my last bullet point to talk through. What are the clues in the context of a particular situation that suggest the use of a particular type of function as a model? So we've got 4 different choices. What are the clues? What are we looking for? So if we expect each new, I don't know, piece of data to fall in line to be linear, then you know we have a linear model. If we expect each new piece of data to be a multiple, let's see. Each new piece of data to be a multiple of the previous piece of data. Previous, oh my, I'm sorry. Previous data, then we would probably try exponential. You know, if we expect, let's see, if we look at the second differences and it's constant, then we do quadratic, right? And then something that's periodic or repeatable, if we can see a repeat in the data, then we're going to try sinusoidal. Right? So that's what, I mean, you just have to look at the data and say, like, what am I looking at, right? All right, so let's try one. It's been long enough of you watching me write. So the table below contains the number of daylight hours in Oslo, Norway on the specified dates. It's nice that they took our hours and minutes and converted it into fractions of an hour, because this is what we want to graph. So I just graphed 8, 9, 10, and 11 for the months and the hours in Desmos. So I just plotted the points, right? What do we see here? Part A says plot the data on the grid provided and decide how to best represent it. So I see a line, which I know, like, that doesn't seem quite right, does it? I can draw a line right through this thing. But would daylight hours be linear? If it were linear, that means as my months continued, I would approach 0. Like, I would have 0 daylight. That certainly doesn't make sense, does it? That would be my trend. As my months get, as x approaches infinity, my function is approaching 0. So linear cannot be correct, can it? So that certainly doesn't work. But I can do some type of sinusoidal. I'm going backwards though. And I'm just totally guessing on where that's going to go, right? I mean, once we hit, this would be November, once we hit December, we're probably going to go back up because the days will get longer as we get closer to spring. But this would be, you know, January, February, March, April, May, June. Okay, June and July are the peak of our daylight hours. So it sort of makes sense that we're sinusoidal, right? It appears to be in a straight line, but that just doesn't make sense, does it? So looking at the context in which the data was gathered, so that's what we look at, context. What type of function should be used to model the data? We've only been given a small piece of the data, that's why it looks linear. We didn't get all of the data. So the context is daylight. Well, daylight increases and decreases with each season. It's very short in the winter and much longer in the summer. So this data, the periodic function for this data just makes a lot better sense, correct? Do we have enough information to find a model that is appropriate for this data? Either find a model or explain what other information you would need to do. Not really, because we don't have any trend downward. So we really don't have enough information to find a complete model. We don't know the maxima or the minima of the data yet. I mean, we know that the total maximum we're going to get is 24 hours, but that's not possible, right? And the total minimum we're going to get can't go past 0, but that doesn't quite work. What you can do is using your stat plot, sine regression on your calculator, you can get an estimate of your periodic function. So you can plug all the data in, you know, your 8, 9, 10, and 11, and the hours, and let your calculator do a sine regression. So that would work. You can go ahead and try it. I can tell you that the answer is close to and your calculator may spit out something close to this. I would not be able to do this by hand, though. Okay? Yikes. Okay, now we do have 6 exercises. I'm probably not going to talk through each one, but I will write your answers in so you can read through them on your own. If I talked through each one, the video may grow to be like forever long, which doesn't seem like a good idea. So again, we're picking our 4 different models, and I have 5 different exercises. So we'll be repeating some, right? So I'm going to go ahead and push pause. As I've paused it, go ahead and read the problem, and then we'll talk through it just a little bit. So the goal of the U.S. Centers for Disease Control and Prevention is to protect public health and safety through the control and prevention of disease, injury, and disability. Suppose that 45 people have been diagnosed with a new strain of the flu virus, and that scientists estimate that each person with the virus will infect 5 people every day with the flu. That's exponential. We know that because each person infects 5 people every day, the number of infected people is multiplied by a factor of 5 each day. Remember, those were some of the clues, some of the characteristics. When something's multiplied by a factor each time, then it's exponential. Do you have enough information? Yes, we know the initial number of people, and we know what the multiplier is. So we can write a function. And our exponential function is always initial times multiplier raised to a power. Okay, here it's time, and time equals day. Okay, go ahead and read it. I'm going to push pause, and then we'll talk through it briefly. All right, an artist is designing posters for a new advertising campaign. The first poster takes 10 hours to design, but each subsequent poster takes roughly 15 minutes less time than the previous one as he gets more practice. What type of function models the amount of time needed to create posters for time is less than or equal to 20? Explain how you know. First poster takes 10 hours, but each subsequent poster takes roughly 15 minutes less time. Okay, here's our linear difference. Our second differences for this problem our second differences are linear, therefore it's quadratic. When it's quadratic, we set up a dummy quadratic equation, just standard form, ax squared plus bx plus c. And we have enough information to solve it. So we know that for time equals 0, we've created 0 posters. For time equals 1, it takes 10 hours. For poster equals 1, it takes 10 hours. For poster equals 2, it takes 15 minutes less, etc. We only need 3 points because when we have 3 unknowns in an equation, we only need 3 equations to solve it. So let's go ahead and solve this. I'm going to work through this one while talking in hopes that it reminds you how to solve equations. So I've got 3 equations, 3 unknowns. So first let's plug in 0 for n, and I get 0 equals n squared is 0, so my a term is gone, my b term is gone, my c term is 0. Now how about for n equals 1? That means I'm going to have 10 equals n squared is 1, so a times 1 plus b times 1 plus c, which is 0, right? And then for n equals 2, I get 19.75 equals 4a plus 2b plus c, and c is 0. So if you remember, we can solve these using just elimination and adding and subtracting the equations together. So a process of elimination. Or, if you remember, we can use matrices in our calculator. If you don't remember how to do matrices in your calculator, please ask, because it's so much easier than adding and subtracting these things. But I'm going to go ahead and copy this onto a new slide and work through the solution. Okay? But I'm going to push pause to do so because it may take just a little bit of time. Alright, that one wasn't too bad. So check through the work, push pause, and see what happened, and we can answer any questions tomorrow. Okay, next, a homeowner notices that her heating bill is the lowest in the month of August and increases until it reaches the highest amount in the month of February. After February, the amount of the heating bill slowly drops back to the levels in August, and then it begins to increase again. The amount of the bill in February is roughly 4 times the amount of the bill in August. What type of function? I got periodic, a sinusoidal function, because it repeats. We've got a maximum and a minimum, and it repeats. I'm going to write that down, though. Hold on. So part B, do you have enough information to find a model that's appropriate? No. They didn't give us any data, so we can't really find a model. But that's okay. Yeah, if we knew the maximums, the minimums, and some of the temperatures in between, we could do it. But they didn't give us any. So nope, we do know what type of model it would be. And if we had some information, we could use our calculators and come up with a model or a function for it, but we can't. 5, an online merchant sells used books for $5 each, and the sales tax rate is 6%, the cost of the books. Shipping charge is a flat rate of $4, plus an additional $1 per book. So we have a lot of per book charges. So we know that we've got $5 per book. Oops. $5 per book, and then we're going to multiply that by a tax rate. Our rates, if our rate is going to add money onto the cost, we do 1 plus 0.06. I'll rewrite that for you. And then the shipping is also a per book. So 1x and flat rate of $4. Okay, this all looks very linear because everything is a per book cost. So it's a linear function. Total cost of everything increases per book at a constant rate. It's not like it's an additional $1 per one book, $2 for 2 books. Well, that would be $1 per book. You know, $4 per 2 books, $10 for 3 books, etc. It's a constant rate. Everything increases per book. Do we have enough information? We do. We know that we sell our books for $5 each, which would be 5 times X. We get charged a sales tax of 6%, which is 1 plus 0.06. We also have a $4 flat rate for shipping plus $1 per book. So this would be the cost per book. Probably could have used a different variable than X. I can collect like terms and simplify it. 1 plus 0.06 times 5 gives me 5.3 plus 4 plus x, that is 6.3x plus 4. That would be my linear function. Last one, a stunt woman falls from a tall building in an action-packed movie scene. Her speed increases 32 feet per second for every second she is falling. So 32 feet per second. Wow, that's fast. Her rate at which she gets closer to the ground increases linearly. Thus, we model it with a quadratic function, right? So I know that's sort of hard, but that's that second difference thing. For every second she's falling, her speed increases by 32 feet per second. So her rate of increase is linear, even though she is increasing. So that is our quadratic function. So do we have enough information? Unfortunately, we don't. We don't have enough information. All we know is the rate at which her speed is increasing, but we don't know how high the building is. We don't know how far she's going to fall. So we don't have enough info. Cool? All right. So just a little review. Okay, go ahead and read through. Moving on. Trying to speed this up, sorry. How is a quadratic model different from an exponential model? So quadratics have maxes or mins, exponentials are unbounded. A quantity increasing exponentially eventually exceeds a quantity increasing quadratically. How is exponential model different from a linear model? All right, there you go. Push pause and read through it. How is a quadratic model different from a sinusoidal model? There you go. One more, right? How is a sinusoidal model different from an exponential model? Okay, sinusoidal is bounded and cyclic. It's periodic. Exponential either goes to a positive infinity or a negative infinity, or it goes to a constant value as x approaches infinity. And that's really it. Okay, I think I have a table. Yep, next slide has a table. So enjoy your problem set. I thought it was sort of fun. I hope you like it. Thanks.